a very short introduction about shear and punching shear provisions in the new model codes. Then Professor Viktor Sigrist from the University of Hamburg, Germany, will continue on shear, and then I will then talk a little bit about punching shear. Of course, the provisions for shear and punching shear are very much related. This is why we have combined our presentations. We have many type of structures where shear problems can be governing. Typically, we know in a girder, in the web of a box girder or a girder with an open section, we all know that this is a typical region of our structure which has to be designed for shear. But there are also other structures which are perhaps a little bit less common, where also shear can be governing. Typically, a cut and cover tunnel, we have the slabs and the footings, which are where the loadings can be very important, and where we usually don't use shear reinforcement. And in these cases, typically shear can be governing. It has, or at least it has to be checked. Another topic is what happens with flat slabs. Let's say slabs supported on column. We know that in this particular structure, the shear forces are not parallel. We don't have a one-way slab. We know that in this particular case, for instance, for the inner column, the shear forces are oriented toward the column. And in this case, we can have significant shear forces, and also in this case, of course, shear has to be checked. In this case, we speak about punching. We have then other cases where we can have both problem very related. Let's say, for instance, the deck slab of a bridge, which is submitted to concentrated loads. In this slab, we can have this zone here between loading and the web, where also shear can be governing, but we can also have the portion of the slab around the concentrated load, where we also can have potentially a punching problem. Which means that when we speak about shear, we need to have provisions which are valid not only for this very classical case, but all these cases here. And these are just 4 examples. There are many many other cases where we can have shear problems. We always have to do the distinction between shear of members without and with shear reinforcement. Why this distinction is important? The main reason is that the failure mode of members with and without shear reinforcement can be completely different. Here we can see a girder, let's say a beam, without stirrups, without shear reinforcement, and we have this typical failure mode here, where we have a very high strain localization. We have at the just before failure, there is one bending crack which opens more than the others, and then it propagates into the compression zone, and at the end we have failure due to the large opening of this critical shear crack. This is what happens in beams without shear reinforcement. When we talk about slabs, and we under concentrated loads or supported on columns, we have a very similar failure mode. This, what you see here, this is just a slab which was supported on this column, and it has been so cut after failure. What you can see here, this is the typical punching cone. It's very similar to this. It's very much related to this shear, critical shear crack. It means that we have similar failure modes, very similar failure modes for shear and for punching, but we still have differences, which means that we have decided in the new model code to propose provisions for these two cases, which are similar but not exactly the same. I will explain later on why it is not possible to solve shear and punching shear in exactly the same way. When we have members with shear reinforcement, then we have quite different failure modes. This is, for instance, this is a girder where we have a crushing of concrete in the web. We see that here, in this case here, the failure mode is very much related to crushing of concrete, and it's very much related to concrete compression strength. When we have slabs and we have punching shear failures, the failure mode can be completely different in this case. We have no analogy between the girders and the punching shear failure. This is very much related to the fact that we have here a distributed stress field and a distributed strain field, and at the end we have a large portion of the web where we can have failure of concrete. In slabs, it is complete. In slabs submitted to concentrated loads, when we have punching, the situation is completely different because we have a localization of stresses and strains, which means that the failure zone is very much localized around the column. You can see from these two pictures then that the situation is completely different, and which means that we cannot use the same provisions for shear, let's say for one-way shear in slabs or for shear in girders, and punching shear in slabs. We will switch now to the shear problem, and Professor Sigrist will continue our presentation, and I will then continue the presentation on punching.
Yeah, thank you. Yeah, ladies and gentlemen, I'd like to put one remark in front of my presentation. We have been a very small working party that worked on that problems, shear, punching shear. These have been 5 people basically, which was Aurelio Muttoni, Miguel Fernandez Ruiz, Evan Benz from Toronto, Stephen Foster, and myself. This small party was involved in the basic work, and we also had some kind of development within the period of work. Means that, as you may realize or may have realized, there are improvements between the first draft of the code and the final thing. So there are several different versions, so to say. At the very end, we are quite happy, and Aurelio Muttoni already mentioned, there still is this kind of difference between the punching phenomena and also the shear type of failure, and this is also, this can be seen and is still found in the code. Okay, thank you. What we did, and now I'm with my subject here, shear in beams and slabs. What we did, we tried to bring different approaches together, different ideas together, which basically included, and we have heard about this earlier this morning, which included to combine our more European-based ideas of equilibrium models, plasticity-based models, bring closer together what we know from Canada, for instance, with the modified compression field approaches. So to have these two traditions closer together. This was one attempt that we found was important. We also, which would be one of the important steps forward, we also tried to come up with a proposal, and this is then the same for all types of shear failures, with a proposal that includes the deformation state in the definition of the strength, which is quite new. This is the difference from the traditional models we know. So, but basically, we attempted to find a model, a physical model, or physical models, several models, that can be explained, understood, and justified. This was our main goal. So, for shear, this started, for instance, with the definition of a control section, as you find right here on this picture, a control section, fixed distance from the support line or fixed distance from a load. And we also brought up some rules on how to deal with uniformly distributed loaded and point loads, which is important to do so. We, as I mentioned before, we tried to found all our models, all our things on the classical things also. Means that the traditional models we know, brought up 115 years ago by Ritter, for instance, the classical truss model was still in our mind. These models, Ritter was one who invented that, have been further developed, for instance, by Mersch, but these models have been classical, which means with a fixed angle orientation for the struts, and have been modified and improved in the late 60s, early 70s by Nielsen, for instance, or the Thürlemann group in Zurich, Nielsen in Denmark, have improved on in the course of the findings of the new developments within the context of plasticity. So theory of plasticity somehow gave a rational foundation to those more empirical models or empirical findings from the older days. So, and all these kind of things, it's one development line, all these kind of models are based on equilibrium, which still is one fundamental, or the most fundamental thing we wanted to achieve also for the new models. These new models, or the results of such a new of the model code definition of the shear strength, can be seen in this diagram, and I'll explain it. We do have, on the horizontal axis, we do have the reinforcement ratio, which is the amount of reinforcement, of the stirrup reinforcement. Here the definitions as a mechanical reinforcement ratio. And on the vertical axis, we do have the shear strength, which is the tau, as we call it, or the shear force divided by the web area. So, and you realize that this is quite normal. For low reinforcement ratio, we do have low shear strengths, and for high reinforcement ratios, of course, the strength increases. We do differentiate between several or different failure modes. We do have a minimum shear reinforcement, which indicates that as soon as we do not put in such much as the minimum reinforcement, there is no shear resistance, or there is only the shear resistance provided by the concrete, which is a different type of model. I'll show you afterwards. And after this minimum reinforcement, this is this vertical line here, the vertical end of the red curve, we do have some kind of a straight line which indicates the theta minimum, which is the minimum inclination of the concrete struts, of the stress fields, so to say. You see here a stress field, it's a fan type of stress field, and you see here the inclination theta, which is meant by this inclined line. After reaching that curved portion of the curve, we are in the web crushing criterion, so to say, means that in that range of reinforcement ratios, the failure is governed by web crushing, which is exactly that type of failure Aurelio Muttoni just mentioned before. And after having reached the maximum value here at 45 degrees of inclination, we are not able to further improve the resistance or increase the resistance. So we do have these different types of failure. What we did in addition in the model code, we added with respect or on the basis of the modified compression field approach, we added some concrete contribution, which is this blue additional triangle, which is an additional resistance for low stirrup reinforcement ratios. So there you see this combination of classical truss model and modified compression field theory. As I said before, we also tried to introduce, and this is quite new in design practice, I would say, we try to introduce the deformation state in definitions of strength. Classically, we do have stress limits, which says such and such megapascal is the limit. We still have such, of course, but here we try to achieve more refined findings, which is including the strain state, the deformation. This holds true for the shear strength, as I will explain right now, and it also holds true for the punching phenomena, where strains are expressed as crack width, but it's basically the same idea behind. Mentioned before, we do have a control section, which is that line here at a distance d from the face of the support, and we do have to transform sectional forces, which is moments, normal forces, and shear forces, into, with reference to the central line, which is at Z divided by 2, which is the mid-level of the girder. And for that mid-level, we do have to define the stress state. And we, as it's quite a complex kind of, could involve quite a complex kind of calculation, we try to simplify this and ended up with this proposal to have this triangular strain profile, which is a linear strain profile, assuming zero strain, zero compressive strain at the compression chord and a maximum strain at the tension chord. So, and from this strain profile, from this linear line, we directly find an expression for the average strain, which is this amount here at mid-height of the girder, the average strain due to bending, due to the influence of shear force, due to an influence of pre-stress or normal force. Both of these amounts are included in the normal force, and we find with one single rather simple equation, we find some expression for the strain state, which is new, which is something special. And we also have, also from this linear strain profile, we do have a definition for a inner lever arm, which is the Z value, which is the distance from the compression and the tension forces. And we also have a definition in case where we do have mixed reinforcement, means we do have mild steel reinforcement and pre-stressing. So both of these expressions, epsilon x and z, come from the linear strain profile. There's nothing special. You can find it by just working through the equilibrium equations. For the resistances, we do have two criteria I mentioned before. We do have number one, which is basically the resistance provided by the stirrups. The very well-known equation coming from the truss model, which includes the amount of stirrups. This is the steel cross-sectional of the stirrups, and the yield strength, the yield limit of the stirrup steel. And we do have this web crushing criterion, which is exactly this type of failure where the concrete fails in compression in the inclined struts. We do have also quite well known from the truss model analogy, we do have this kind of equation, FCK divided by some safety factor, and we do have the influence of the inclination, which is sine theta cos theta. But we do have a reduction factor, as you all might know, similar to what you know. We do have a reduction factor which, this is new, which includes this strain effect, which is the K epsilon, the first part here, and also includes the brittleness influence, which is this second part here in this equation. For these two things, we had to go back to literature, and we find, for instance, we find for the strain effect, we find several proposals in the literature. For instance, there is one very famous, very important proposal, which comes from the modified compression field theory. We had to modify this a bit due to the fact that we are dealing with webs and not that much in panels, which is kind of a difference, more complicated strain state, and we came up with that proposal, which was found by experimental comparison with experimental data, of course. On the second hand, or on the other hand, we do have this brittleness effect, which is a proposal by Aurelio Muttoni quite some time ago, where he found that there, of course, is an influence on the brittleness with regard to the strength of the concrete, and that with this rather simple equation, this effect that the higher the strength, the more brittle the behavior can be captured. So these two effects, again, together are composed or are part of this reduction factor, which reduces the strength in the struts. So, and as mentioned by Joost, Walraven this morning, we do have several levels of approximation. We do have a low level, a first level, level 1, which should be or thought to be used for conception of structures, which should be used for first design, for a simple approach. And we always have those two, as my first diagram should have been shown. We do have these two things to distinguish, to differentiate. We do have the theta min question, minimum inclination of the struts. It's the minimum. We always have to choose between the minimum and the 45 degrees limit. And on the other hand, we do have this reduction factor, just explained before. For level 1, we do have given fixed values of theta min, which is 25 degrees for pre-stressed members or 35 degrees for ordinarily reinforced members. And we do have a constant reduction factor, which is 0.55 times the brittleness influence, which ends up in a straightforward possibility for the design. It's very simple. It's rather on the safe side, but it's straightforward. It's easy to apply. For the second level, level 2, it's thought to be used for the detailed design or an assessment of a member. We do have a bit more complexity in the procedure. We do have to the chance to calculate the theta min, which is not anymore fixed values, but rather calculated values as a function of the stress state. Here you find the epsilon x again. So it's not too complicated, but rather more complicated than level 1. And we do also have a non-constant reduction factor, means this Kc value is a function of the stress of the strain state as well. So we do have a more complex procedure. For level 3, which is the highest level in the analytical world, so to say, we do have, it is thought to be applied for the design of very complex loading states or an elaborate assessment of a member, we do have an additional contribution. As I mentioned before, this is the modified compression field part of the shear strength. We do have an additional VC term, which is a contribution coming from the concrete. And this VC term is given here and can be calculated and is quite similar to what we will see later on for cases with, for members without shear reinforcement. So, to explain this further on, we probably can go back to the diagram as shown before. We do have reinforcement ratio, we do have shear strength, and we can differentiate between design situations and assessment situation. In this design, we do enter such a diagram. We don't work with diagrams, but it can be explained with help of the diagrams probably. We do enter that kind of thing from the left, which is the VED is given, a tau, the shear force is given, and we do enter such a diagram, and then we choose or select some theta value, which is indicated with this dotted line, and then end up, we choose some reinforcement ratio, and we choose some web width, for instance, and we end up with a certain amount of reinforcement that should be provided. Completely different in the case of the assessment. We do enter such a diagrams from the bottom because the reinforcement is given, the geometry is given, so we do have to enter from here, and then there is some iterative procedure. You can't directly find the solution because the curves are not fixed anymore because there is this strain influence, but at the very end we do find some solution on such a curve, which is drawn here in green. So these are two different cases to differentiate. I would skip this one and would go directly to the case of members without shear reinforcement. I mentioned before the models are similar, are related to each other, but are different, which is due to the fact that Aurelio Muttoni just mentioned that the failure phenomena are different. We do have several, in literature, we do have several proposals how to deal with such things. For instance, there is also a proposal by Muttoni and Fernandez Ruiz, which is based, and this is what we also included in our model, which is based on the definition of a strain state. Number one, very important influence, the strain state. Again, this epsilon x I just mentioned before, as well as the size of the member, which is quite an important difference between reinforced members and members without reinforcement. We do have this size influence. Similarly is what we adopted or included in the code. We based the whole thing on a type of physical model, and again, the remark, it's a strain-based model. We end up with this basic equation, the shear resistance due to concrete, it's only the concrete because there is no stirrup reinforcement, is a function of the square root of the strength, which is FCK, square root of FCK divided by some safety factor, and we do have this KV factor, which can be chosen. One KV we have already seen, which is the modified compression field part in the members with shear reinforcement, and two other KV factors we see right here for members without shear reinforcement. We do have, again, level 1 approximation, which is for the conception or the simple preliminary design, so to say. We do have only these fixed values, where we do have a Z, and Z is the member size. It's the internal lever arm of the member. So here we do have the member, the size effect included, but no strain effect. If we go one step further to level 2, we do have the strain effect included, which can be seen here. It's the epsilon x again, and exactly the same procedure to calculate this epsilon x with the equation shown a few slides before. And we do have, again, the size influence, which is manifested by this Z influence right here. So these two levels are the levels that are foreseen for analytical solutions. In both cases, for members with shear reinforcement and for levels without shear reinforcement, there is a even higher level, which is level 4 for the first case, level 3 for this second case, where we allow people to use nonlinear, finite element or similarly based procedures. But as we have heard several times in the conference already, these also need some good experience, so some deep understanding of how computer programs work. So we do have provided the analytical expressions for the code, which is for a daily use, so to say, but for the experts, the possibility is given to use more complex, more complicated numerical analysis. To compare this, I can show this slide just to give an idea on what's the difference between the results from these two levels compared to Eurocode. Eurocode should be known in the meantime also in this part of the world. It's quite widely spread, I learned. So we can compare such things, and we have produced such a graph for different strength classes of the concrete. We can, for instance, take a look at this right-hand side diagram for FCK of 50 megapascal. We do have these green lines, blue lines, which represent, no, the blue lines represent the Eurocode results, and we do have the green lines, which is 1, 2, 3 different strain states, which represents the results of the model code. As you may realize, the comparison, it's a bit complicated, because in Eurocode we do not have this strain influence, so we do have to help ourselves by assuming certain amount of flexural reinforcement and so on, or even with some amount of pre-stress, which is different from the procedure of what we have in the model code, where we do calculate the epsilon x. But as a general comparison, this may help. Nevertheless, this may help. We do see that on the very low level, on the low side, we do have the red curve, which is the level 1 of approximation, which is comparable to what we have for a very small or low amount of flexural reinforcement in the Eurocode. So similar results are found with that. But for the highest case, which represents some pre-stressed element, for instance, we do have, on the one hand, more strength predicted by the model code compared to Eurocode for smaller size members, and we do have lower strengths for bigger size members. So we realize that the size effect is a bit more pronounced, or what we do in the model code is a bit more pronounced with regard to the size effect. So I also want to just to show you, to give you an idea, it's not only a theoretical work we did for the model code, we also did some quite comprehensive comparison with experimental data. And here you see for the members without shear reinforcement, we included some 800 and something beam results to compare, and different levels give different results. And for the members with shear reinforcement, we included some 250 or something beam results, and we do have this kind of comparison. One last slide from my side, and then I give over to Aurelio again. And Joost already mentioned it. For the first time, we do also have the chance to include this, the effect of concentrated load on slabs. It's a preliminary proposal, so to say, because there still is research going on in that field. It's quite complex, because it's not only a linear or whatever problem, but rather a lot of influences. But here, and you see Aurelio Muttoni's group in the lab in Lausanne, I guess, where they tested huge slab cantilever slabs of bridge type structures, and from such experiments we developed this first proposal to include this effect. So just to give you this information again. So this is it from my side, and I hand over to Aurelio again.
Thank you very much, Viktor. Well, I will continue with the same picture. In fact, when we have the concentrated load near to the support, then we get this kind of shear failures. But when we move the concentrated load on a small area, which acts on a small area towards the free edge, then we can have potentially a punching shear failure here in the slab. This is very much related to what we have in flat slabs. Let's say slabs with constant thickness supported on columns. The procedure to check punching shear strengths, I will start with members with slabs without shear reinforcement, is very similar to other codes. In fact, we calculate the punching shear capacity multiplying the length of control perimeter, which is defined as a perimeter located at a distance 0.5 from the edge of the column. We have to multiply the length of the control perimeter by the shear resistance effective depth. I will come later to this parameter here, and this parameter here, which is a shear strength in megapascal. This is very similar to other codes, of course. To the control perimeter, as I said, it is located at 0.5 D from the edge of the column. This is quite different compared to Eurocode, as you can notice. It's very much, it is similar to the ACI code. We have done a lot of investigation, and we have seen that this choice has many advantages. For instance, we can use exactly the same provisions for flat slabs and footings. If you don't have this assumption, for instance, like in Eurocode, we cannot use the same provisions. We have to adapt the provisions, the punching shear provisions for footings. There are other advantages. We have not the time to discuss them this morning. There are other advantages choosing this location of the control perimeter. When the loading and the geometry of the slab is completely symmetric, then we can take into account, we can take the full length of the control perimeter around the column. When we have unbalanced moment or when we have non-symmetrical cases, we have to reduce the length of the control perimeter. There are quite simple provisions in the new model code in order to calculate this reduction perimeter. We have also, for this case, very similar provisions in other codes, but we have tried to simplify them, and we have found that this proposal is much more simple compared to, for instance, what we have in ACI code or in Eurocode. We have introduced the concept of shear resisting effective depth of the slab. This is important only when we have a variation of the thickness of the slab in the shear critical zone. For instance, such a wall or such a slab which is suspended by a tie, it is clear that only this portion here of the slab will assuming this, this relationship. And then there is this very important factor here, which is a reduction factor in order to take into account different parameters. Let's explain this, this influence with this slide here. You can see a saw cut of a slab here. We have usually the shear, which is carried by this inclined strut. This is the old Kinun and Nylander model. It's a very old model proposed about 50 years ago, which provides quite good results. The new idea integrated in this provision is that the shear force which can be carried by this theoretical compression strut can be reduced by the presence of a shear crack which starts at the very beginning as a bending crack. And this is, in fact, this is the main idea. We have something which is very similar to the approach for beams without shear reinforcement. There we have assumed that we have a crack opening, and we assume that we have a strain which produces this crack opening, and we assume that the shear strength is directly related to the opening of this shear, at the very beginning of the bending crack, and then it propagates into the compression strut as a shear crack. We have done many theoretical calculations. There are, for instance, physical models which allows us to calculate shear which can be carried across this potential critical shear crack as a function of the crack opening and as a function of the roughness of this critical shear crack. For instance, Joost Walraven has presented this morning one of these possible models. We have used it in our theoretical model, exactly the same model which has been presented this morning by Professor Walraven, and what we get is something very interesting. You can see the result of the physical model. This is the shear capacity of the slab as a function of the product of psi, where psi is the rotation of the slab. It is an angle which is due to bending deformations. We have opening of many cracks here, which provokes a deflection of the slab, and the deflection in the middle is related to an inclination of the slab here. It is what we call this rotation psi. The assumption which we have done is that the crack opening in the critical zone is related to the product of this rotation times the thickness of the slab. This is why we have in the abscissa of this diagram the product of rotation psi and dimension d. This is the statical depth. We have also seen that roughness of the crack has also an influence on the shear capacity of the slab, and we always know that we all know that the roughness of the critical shear crack depends on the size of the aggregate, and this is why we divide this nominal crack opening by the size of the aggregate plus a reference size of 16 millimeters. It is interesting to know that we have performed here many calculations, many theoretical calculations, and one can see that with many parameters, for instance, with many bending reinforcement ratios, many thicknesses of the slab, many sizes of the aggregate, and what we can see is that the difference is quite small, which is very useful for design, because we can simplify this failure criterion here by an equation which I will show later on. Here on the right-hand side of the slide, you can see a comparison with test results. There are many test results which has been carried out in many countries in the last 50 years, and this comparison shows that the theoretical calculation fit quite good the experimental results, which means that for engineering calculation, for designing, or for assessment of an existing structure, what we can do is we can take such a curve where we describe the punching shear strength as a function of the product of psi and d. Please note that we have combined psi, which is related to a strain in the governing region, in the critical region of the slab, and d, which is the size of the slab, as already described by Professor Sigrist. We have in these problems where we have a localization of strains always a size effect, which means that if we double the strength, the thickness of the slab, we will get a punching shear strength which is less as the double of the previous slab. This is what we call the size effect. This is again the comparison with the test results. We have a small scatter which we can take into account using a characteristic curve here, assuming that we don't have more than 5% of the tests which give a lower results than what we have proposed in this equation here. And this equation here, it is exactly what we can find in the punching shear provisions of Model Code 2010. It is exactly what we can see here. It is the same equation. Now, when we want to calculate the punching shear strength, the punching shear capacity of a slab, we need to know the thickness. This is well known, but we also need to know the rotation psi, because we have a strain-based model. And for this case here, it is a little bit more complicated than in shear. Please note that in shear we have elastic behavior of reinforcement. It is usually not the case in punching of flat slabs, because we have very large concentrations of moment around the column, so that we, at the ultimate limit state, in many cases, we have yielding of reinforcement, we have plastification of reinforcement, which means that the stiffness of the slab here is not constant. At the very beginning, reinforcement is elastic, but as soon as we have yielding of reinforcement, then we reduce the stiffness of the slab, which means that rotation psi will increase much more than the load, or let's say the shear force. This is why we have to take into account this nonlinear curve here for the calculation of psi. It is possible to calculate, in fact, it is possible to calculate rotation psi doing some assumptions and take into account a nonlinear moment curvature relationship. We have seen that this is very interesting for research purpose, but it would be it would be too complicated for engineering work, and this is why we have simplified the curves which we can calculate using this model here. We have simplified these curves by this equation here. The parameters are derived directly from the theoretical model. We can find an explanation in this paper here, which has been published last year on structural concrete, which is the background document to the punching shear provisions. You can see in this paper that we can get this equation just taking these parameters here from the theoretical model and then simplifying this relationship here. Let's say this is the punching shear strength. This is the red curve. This is the which is given by this parameter key psi. And in order to calculate rotation psi, we need to know this view curve here, which is given by this equation here. You can see in this slide the parameters which influences the rotation psi. We have the most important one, which is the slab slenderness. If we increase the slab slenderness, then we increase deformations, of course, and we increase rotation psi. This parameter here is related to yield strain of bending reinforcement. And this parameter here, this function here, takes into account the level of utilization of bending reinforcement. If you increase the utilization of bending reinforcement, we increase the strain in the reinforcement, and we increase the opening of the critical shear crack so that we increase rotation psi. And this is taken into account with this curve here, where we have this failure criterion. There are some proposals for using the level of approximation approach. The level approximation approach is very useful for punching because in many cases punching is not governing. Let's say, for instance, in bridge slabs, if the thickness is enough, in many cases punching is not governing, which means that it is very useful to have a very simple tool and to perform a very simple calculation. There are also similar situations in buildings when for the choice of the thickness of the slab, deflections are governing, or vibrations are governing, or other criteria are governing. And the size of the column is also enough because other criteria are governing, for instance, normal force capacity of the column. Then we have sufficient, in any case, sufficient punching shear strength, which means that in these cases it is very useful to have a very simplified approach. And this is what we call the level 1. This is usually used for when the punching is not governing or for preliminary design. When it is governing, then it is useful to have a more refined calculation tool, and in some cases it is even necessary to do a more refined calculation. For instance, when we wants to assess the strength of an existing structures. It has been described many times during the last days. It is very useful to have more refined calculation tools. You see the level of approximation approach in this on this slide here for the two parameters which are usually a little bit more difficult to calculate for our flat slabs. The bending strength, the bending capacity, of course, it varies to calculate. This is known. The statical depth is also known. The only two parameters which are a little bit more complicated is RS. RS is the distance between the axis of the column and the point where the radial bending moments are 0, which is the contraflexure point. This can be calculated, for instance, with a finite element, with a linear one, which is usually used for designing bending reinforcement. But in order to allow a simple calculation without doing a bending analysis of the slab, we propose this very simple relationship. It is a simplification of the reality, of course. We assume that the distance between the axis of a column and the point of contraflexure is 0.22 times this pan L. At level 1, we can also assume, and this is always on the safe side, that all the reinforcement on the support strip is in yielding, which means that this ratio here is 1. It's what we assume at level 1. It is on the safe side, of course. If the strength is not sufficient, we can perform a more refined calculation. In this case, we can calculate an average moment on the support strip as a function of the shear force and of an unbalanced moment if it is present. And even in this case, if this punching shear strength is not sufficient, then we can perform a calculation at a higher level. This would be the level 3, where we calculate the position of point of contraflexure and the average bending moment on the support strip, just using a linear elastic uncracked model, be a finite element model usually. Just few words about punching with shear reinforcement. This is, of course, an important topic. If punching shear strength is not sufficient, we can increase it, providing punching shear reinforcement inside the slab. In this case, we have 3 completely different failure modes which are possible, which means that we have to perform 3 very different calculations. The first one would be related to crushing of the first strut. The second one would be an opening of a punching cone with activation of the punching shear reinforcement. And the last one would be punching outside the punching shear reinforcement. As I said, we have to calculate, we have to check all these 3 potential failure modes. The first one is very simple to calculate. We just use exactly the same equation for punching capacity without shear reinforcement, and we multiply these strengths here by a parameter K system, which is related to the type of, is a function of the performance of punching shear reinforcement. There are punching shear reinforcement, for instance, like shear studs, which are very efficient because we have a very efficient anchorage. There are other reinforcements which are less efficient, and we can take into account this effect, assuming different values of this parameter here. For the second failure mode, it is a punching with an opening of this critical shear crack and an activation of punching shear reinforcement. For this case, we assume that the shear force can be carried by combination of 2 different mechanism. The first one would be the concrete capacity, which is still possible, and the second one, of course, is the activation of the punching shear reinforcement. For the component related to this compression strut, we use exactly the same equation, exactly the same approach as I have shown for slabs without shear reinforcement. We just add the component of the punching shear reinforcement, and this is perhaps something which is very new. We have seen in many tests that if the slab is very stiff, we have relatively small crack openings at just before failure, which means that we cannot activate yield strength in the punching shear reinforcement. We have based our calculation on a very physical model which allows us to calculate the stress in the punching shear reinforcement as a function of rotation psi. It is logical. If we increase the rotation, we increase the opening of the critical shear crack, which means that we can activate more force in the punching shear reinforcement. But of course, if we increase the crack opening, we also reduce the component of shear force which is carried by concrete. It is exactly the blue curve which I have shown before. For punching outside the shear reinforcement, this calculation is important in order to know how wide has to be chosen the zone in the slab where we need punching shear reinforcement. For this calculation, the principle is exactly the same as for punching without shear reinforcement, with the only difference that we reduce the effective statical depth. You have perhaps seen that there are some points which are a little bit different compared to other codes, for instance, ACI codes or Eurocode. There are we use now models which are much more physical, and in order to help engineers understanding better how they have to perform calculations, we have produced a document which can be downloaded from this site here, where we explain how the punching shear calculation can be done for a very simple case, but a very common flat slab. We start with level 1. The idea is, as I have shown, is that the calculation is very simple. We calculate the length of the control perimeter, the position of the point of contraflexure. We estimate rotation psi on a very safe manner, and then we calculate this reduction factor, which takes into account the size effect and the strain effect, and so that we can calculate very easily punching shear strength. If it is not sufficient, then we can go to the level 2, and the main idea of the level of approximation approach is that we keep as much as possible parts of the calculation done at level 1. This is very important. It is not necessary to repeat all the calculation. Many parameters here can be kept. We have just to increase the precision of some important parameters, like, for instance, what you can see here. I have here now in red what is new, in green what has been performed at level 1, and you can see that there are just few parameters, just 2 parameters which can be improved. For instance, the first one is taking into account the level of strain in the bending reinforcement, which means that we have to estimate the average bending moment in the support strip. We have provide equation in order to estimate this average bending moment, which allows us to estimate rotation psi with a much better precision. We put this new rotation psi into this equation here, and then we get very quickly this reduction factor k psi. And also here you can see that some parts of this equation, some parameters are kept from the previous level of approximation. We can do exactly the same at level 3. For instance, we can perform an elastic finite element calculation of the slab, and then we can calculate very easily the position. We know very easily where the bending moment is 0, which is given by this parameter r here. And we can also calculate the average bending moment on the support strip, which is this value here. If we put these two new values in the old equations, we get very easily a more precise rotation psi, a more precise parameter k psi, and a more precise strength and punching shear capacity. As you have seen, perhaps, the very new approach is that we based our provisions on a very physical model. We don't use anymore the empirical equations which has been used, for instance, for Eurocode, and this has many advantages. For instance, we can use exactly the same approach, exactly the same provisions for cases which are even not foreseen in the code. Where, for instance, we have used exactly the same principle for slabs which are retrofitted using carbon fibers or using post-installed shear reinforcement. I have not the time this morning to explain how it works, but it is it's very logical, and it is based completely on the same provisions you can find in the model code. We have used also exactly the same approach for fiber concrete. In this case, we use exactly the same approach as in slabs with shear reinforcement. We have the component of the shear force which is carried by concrete, and you have just to add the part of the shear force which can be carried by the fibers. We have used, for instance, the provisions which we can find in the model code, combining the activation of the fibers with this physical model developed by Professor Steve Foster and his co-workers. It would be also possible to use the method for fiber concrete, which will be explained by Professor Di Prisco this afternoon here in Mumbai. And if we combine both models, we get excellent comparison with test results. This is using the model code provisions, and this is using empirical models which can be found in literature. As you can see, the scatter is much less, which means that this model is also very useful for fiber reinforced concrete. The last case I would like to just to present very quickly. There has been a presentation by Dr. Fernandez Tuesday on the differences between isolated elements. As you know, all the code provisions are calibrated on laboratory tests, and many of the laboratory tests are performed on isolated test specimens. We have seen that there is a very important influence of membrane action in actual flat slabs. We have used exactly the same model and taking into account the influence of membrane forces on the load rotation curve. As you can see in this diagram here, if we take into account the full slab around the column, we increase the stiffness, which means that we reduce rotation psi, we reduce the crack opening, and we increase the punching shear capacity accordingly. This increase depends, of course, very much on the different parameters. There are situations where this increase is not very large, but there are other cases where this increase can be very important. I would like to conclude my presentation. As you have seen, the new provisions for shear and for punching shear, they are grounded on consistent mechanical models. This is very important in our opinion, but they have also been checked against extensive experimental data. All around the world we have found very interesting tests which we have used in order to perform these comparisons. The accuracy of the mechanical parameters can be progressively refined in various levels of approximation, and this is very important in order to be able to perform very simple calculations, but also with exactly the same model, very refined calculations, which are very important for assessment of existing structures. And another point which is also very important, in my opinion, these provisions can be easily adapted to unusual cases, providing the designer with a clear understanding of the structural behavior. Thank you very much for your attention.
Generally, flat slab is designed with linear variant elements, slab elements or shell if you have stress.
Yes.
In the output of the analysis, we have also torque moment around the column. What do we do with this torque moment? We disregard it. Torque moment.
Yes.
In the elements.
Very, very, very good question. Thank you very much for the question. The definition of the average. This is very important. The definition of the average moment on the support strip here, which you can see in this equation here, has to take into account also the influence of torsional moments. But what we do is usually for classical flat slabs with a more or less regular geometry, we perform a calculation in one direction, parallel to the reinforcement, and in the other direction, also parallel to the other layer of reinforcement. And for common cases, the torsional moment on this cross section here, they are neglected. They can be neglected for inner column. This is also the case for edge column. The only case where torsional moment can play a major role are the edge columns. In this case here, I fully agree with you. We have to take into account the torsional moments. This is also one reason why we have preferred to give a simplification equation in order to estimate in a very simple way the average moment on the strip.
Just one very quick comment. It's very relevant, absolutely rational approach, an excellent approach actually the code has taken. To bring it importance, in this city we had a collapse of a 8-story building, which was a flat slab building, and it actually collapsed. It's a building in a state called Shiv Sagar in Worli, and it actually collapsed due to punching shear failure. The whole building.
This is a very important remark. We we have also done comparisons. We have also done comparisons of this model with real collapses, and this is always it's also very important in order to see if there are not hidden additional strengths which we neglect with this approach. And we have seen that we are able to reproduce what happened in real collapses with the model. I would be very interested to have more details on this collapse, because we are very interested to analyze these cases.
Hello, I have a short question concerning the shear load capacity without shear reinforcement. Is there any possibility to calculate the shear load capacity if you have any openings in the slabs? So any utility ducts or something similar? I know the Swiss solution and I know the Eurocode solution, because, but what's in the model code concerning this topic?
It's a question somewhere in between shear in slabs and punching. And of course we do reduce the perimeter, the control perimeter, according to openings and things. Yeah. So there should be. You have it on your slide also? I
don't have it in my slide, but I can try to explain in this way.
Yeah.
If we have, for instance, for punching, but for shear is very similar. If we have radial ducts which converge to the column, then we can reduce the control perimeter. We can assume that the portion where we have ducts, there is no shear force which is carried. If we have, and this is the most common case, if we have ducts which are parallel which are tangential to the column, but first of all, we should try to avoid this situation, of course. But if we have, let's say a duct here, and this is perhaps more important for one-way shear, then what we can do is to use exactly the same approach here, and we can reduce the shear resistance effective depth accordingly. Yeah. We have, you are right, we have some rules in the Swiss code in order to take into account this effect. It has to be done. That it has to be perhaps to be said that the provisions we have in the Swiss code has been adapted in the last version of 2013. Has been adapted from the model code, from the new model code. I think it's probably the first code which uses the model code provisions.
Thank you.
You mentioned the effect of aggregate size on the shear capacity. Usually, whatever I see, that everything is based on 20 millimeters nominal maximum size of aggregates. Now, many times for some reasons, we have to produce concrete with 6 millimeters or 12 millimeters or 10 millimeters aggregates. Will they really reduce the, and of course, the strength remains as we have designated. Will it really reduce the shear capacity in those cases?
Yes, there are many tests which show that the for usual concrete strengths, let's say less than 50-60 megapascal, they show that the size of the aggregate is important on the shear which can be carried across the critical shear crack, and there are many tests which confirm this hypothesis. It has also to be said, when we increase the concrete strengths higher than 60 megapascal, then one can observe that the cracks don't go anymore around the aggregates. They broke the aggregates, and in this case, the influence of the aggregate size is much smaller.
And will you also take up torsion?
Sorry?
Torsional shear.
Torsion?
Yes.
In combined to shear.
Yes.
Yes, of course.
Okay. Fine.
Yes,
Thank you.
there are provisions also for punching in the new model code.
I'm interested about your opinion about the assumption of critical section in case of punching, because I saw in your proposal that this critical section you've proposed like a half of D from the edge of the column, but when you go back in history, I mean in Eurocode or any national standards before the Eurocode, this critical section was implemented from let's say 0.5 to up to 2.5D. What's your opinion about this assumption of critical section?
Thank you. This is a very, very important remark. Let's say there are two phenomena which influence the punching shear strengths, and I think that in the past the provisions for Eurocode has been adapted empirically in order to take into account two very different phenomena. The first one, if you increase the size of the column, of course, you increase the perimeter, the control perimeter, and you increase punching shear strength. This is very logical. Then there is another phenomenon. If you increase the punching shear, the size of the column, you increase the punching shear strength, which means that you also increase rotation. Which means that if you increase the size of the column, at failure you have a critical shear crack which are more open than in the case of a slab with a very small column. And this explains why, if you increase the size of the column, the increase in punching shear strength is less than the increase in the control perimeter. I don't know, it's a little bit complicated to explain, but we have done many calculations which clearly show that we have to take into account these different influences on the punching shear strength. And what has been done many years ago for the old model code, for model code 90, which was at that time the basis for the current Eurocode, at that time it has been chosen empirically. The position of the control perimeter has been chosen empirically in order to take into account these two phenomena, which means that it works quite good for common sizes of column, which has been tested in laboratory. It works quite good for symmetrical cases. It works quite good for inner columns. But as soon as you have other situations, which you also can find in practice, which has never been tested experimentally, then it can be not on the safe side. For instance, there is a research done by Professor Paul Regan in London some years ago, which shows that a recent punching shear test with very small column doesn't work with the provisions of Eurocode, because at that time when the calibration has been made, these tests were unknown. There are other situations where the choice of a control perimeter at 2D from the edge of the column doesn't work. This is the case of footings, or the case of flat slabs, where we have a significant load in the zone of the column. It can be an external load, or it can be the deviation force of a curved tendon. the comparison to test results show that in these situations, the perimeter located at 2D according to Eurocode doesn't work. There are some provisions which has been proposed for the model for the Eurocode, but these corrections are still empirical, and we came to the conclusion that it is much better to have this physical model which takes into account correctly the two different phenomena.
Thank you.
You're welcome.
I have two questions. One is in case of pile caps, where if you have a large column and the column is overlapping the pile, what happens to the punching shear? And another question is in case for columns with capitals.
Yes.
Where should we check the punching shear?
Yes. Very, very interesting question. The first case, when we have pile caps, we have what changes. We have concentrated forces from the piles, which acts very near to the loaded area, which is the area of the column, which means that the distribution of the shear forces is in most cases is not constant. We have to take into account this situation. But unfortunately, we don't have provisions in the model code. I think that in the list of Professor Walraven of problems which needs to be investigated in future, this is a classical, this is a very interesting topic which should be investigated. But I'm quite confident that we can use the same model just with small adaptation and adapt a little bit, taking into account the reduction of the control perimeter. In fact, it is very similar to a footing. Then the second case, what happens when we have capitals, external capitals? We have to perform different calculation, assuming potentially different control section. The idea is that we should, unfortunately, I don't have the picture, but we have to perform, for instance, a calculation outside the capital, other calculations inside the capital. If you are inside the capital, we increase the shear resistance, the shear resisting effective depth. We increase this value here, but we reduce the control perimeter, of course. And then we have to search for the position of the governing control perimeter, which is governing, which gives the smallest punching shear capacity.
Thank you.
Welcome. Yes, please.
I would like to know whether there are any guidelines for design of cantilever slabs subjected to eccentric loading where bending and torsion can be a combined state.
You mean calculation for shear capacity?
Shear and bending.
In fact, it is. It is this case here. It is this case here, and there are interesting provisions in the model code which allows to estimate the length of the control perimeter as a function of the distance between the load and the support and the size of the loaded area. We have compared these very simplified rules with other calculations. They work not so bad, but this is another field, in my opinion, where we need additional work. It has also to be said that there are very few tests which has been carried out on slabs with concentrated loads near linear support, and we have taken into account the tests which we have found in the literature, but I think we still need to perform additional tests because this phenomenon here is very complicated. It is related to the concentration of shear forces over this control perimeter here. Of course, the shear force here is larger than here. If we perform a linear elastic calculation, if we are usually on the safe side, because we don't take into account that at ultimate limit state we have a redistribution of the internal forces. We usually have the beginning of the shear crack, which produces a reduction of the shear force in the governing region here. But this means that the redistribution of the internal forces is very difficult to take into account. And this is why we have proposed this very simplified estimation of the shear force. I think it is the first step. I think it's the first code worldwide where we are able to calculate shear strengths here, but we still need to improve this model here.
And if the load is at the corner, not in the symmetric position, it is very much eccentric on the corner.
For instance, when we have
at the tip at the corner.
The load, let's say here, for instance.
No, at the tip
here.
On the cantilever, yes.
Here, well, a load which is applied here would be very similar to a corner column, which means that in this case we have to check punching shear. We have to check punching shear strength of a corner column, and then we can use without any limitation the provisions for corner columns. I didn't have the time this morning to explain what happens in edge columns and corner columns, but we can use exactly the same model with just a little bit different definition of the control perimeter. But this is clearly described in the new model code.
How do you judge the fixity of the clamp boundary condition? Same the box girder. How do you judge?
Well, this is a good question, but this is related to analysis this is related to calculation of internal forces. We speak here only on the calculation of shear capacity. Of course, I fully agree with you. The calculation of the internal forces, this is another problem. We have to take into account the full cross section of the box girder, and also the position of the loads and related to supports. It can be quite complicated, but this is related to analysis.
Sir, I'm coming back to the question asked by the earlier gentleman. I'm coming back to it again because in practical situations do arise where sometimes the column line area, when superimposed with the piles, supporting piles below, there is a
pile caps.
Pile cap.
Yes.
Through the pile cap, then the piles, and there is a partial overlap of the load.
Yes.
In that case, we understand the answer you have given that more work is required to find out if we are going to use the shear model or punching shear model for that calculation.
Yes.
Till such thing happens, will it be safe enough to use a truss and tie model?
Exactly.
And get if you can't solve a problem, then the wise engineers circumvent it.
Yes, this is a very good remark. If the distance between pile and column is small or even negative, even if there is a superposition of the piles and cap, then I fully agree with you. We are going toward a strut and tie model, and then the question is how to calculate stresses in the strut and how to calculate strains in the strut.
Simple.
And there are some works which has been for instance, done in the United States by Professor Kuchma, where he has proposed some rules in order to calculate with a strat and tie model.
So what I do for purpose of economy, one can throw the economy to wind side and say I will take the entire force in my strat and tie model, which is not simple. The portion which is overlapping, I would assume that much load goes directly as a column and reduce the load on the column for the truss and tie model.
Yes, this is very, I agree, this is usually in the safe side, because you neglect the triaxial situation and the increase of concrete strength due to confinement. But this, I fully agree with you, this is usually on the safe side. There are only cases where this approach is not on the safe side, with pile caps which are a little bit larger, and where the distance between the different piles is too large, which means that the distribution of the forces is not constant. And another problem we can have, if the shear span is large and the reinforcement is not very strong, then we can have at ultimate limit state very important strains, which reduce the concrete strength, for instance, due to the Vecchio-Collins effect.
But just a comment, a rapid comment. But we have to say definitely that we have to change the philosophy in design on Planton piles. Because up to now, with the interaction of piles of 2.5D was governing the strat and tie design.
Yes.
Now that we have the control perimeter to 0.5D,
exactly,
we have to check for punching.
Yes, yes. Which makes the calculation much simpler, in fact, and much more related to what happens in reality. I agree with you, yes.
I think in one of the slides, the effective shear depth, Z, the lever arm, in one of the slides you have shown that it is the distance from the CG of compression to the CG of tension. My question is that in case of, suppose we have an uncracked section under ultimate limit state in shear, then what should be the lever arm?
Yes.
Or suppose in case of a continuous structure, if you have tension.
Good question. The definition of the statical depth is usually the distance between the average position of the bending reinforcement to the compression side. In the case of shear, we have to reduce in these cases here. And the definition is that the shear resisting effective depth, I don't remember exactly the wording in the provision of model code, but it is defined as the distance between the average position of bending reinforcement and level of support. You see, for instance, in this case here, we assume that there is no friction between the concrete and the steel plate, which means that we have to assume that the support of the slab is here.
Excuse me, I was actually questioning about the shear in case of a girder, with particularly pre-stressed girders.
You didn't understand the question, sorry.
So, just to come to short end, hopefully, I don't know. Yeah. There we see, we normally, as already mentioned just now, we normally assume the effective depth as the distance from the compression cord to the tension cord, which is all the same for ordinary structures. And we have to reduce it in cases where substantial portion of the tension force is carried by pre-stressing, where we do have some effects, which is accounted for in this equation, which is given in the code. So this is the short answer for a rather complicated situation. Yeah.
So, thank you very much